All right, so this lecture is meant to be a refresher of all things exponential and logarithm, so expressions, equations, functions. First, we're asked to evaluate each logarithmic expression, simplify fractions. So here I have ln e. Remember that there is a base e, even though we don't write it. So we think of it as e to what power gets us back to e. Gotta be a 1. Okay, here I have log 0.01 or 1/100th. This is a common log. There's a base 10. We just don't write it. Sometimes it helps to view that 1/100th as a fraction. So 10 to what power gets us 1/100th? Well, 10 squared would be 100. So 10 to the negative second power, right there, would get us 1/100th instead. Okay, here, 2 to what power gets us 1/8? Well, 2 cubed would be 8. So this must be to the negative third power. So this would resolve to be just -3. Okay, this next one, I have a square root of 3 in the base. I'm going to visualize that one. So square root of 3 to what power gets me 1/27. Okay, square root, that's the same thing as saying 3 to the 1/2 power. So 3 to the 1/2 x power equals 3 to the negative third power. Once their bases match, their exponents must match as well. So half of x equals -3. Clear the fraction by multiplying each side by 2. And we get -6 right there. All right, next row. Here I have 1/125 to what power gets me 25. Now, if you can see it without this process, no problem. I'm just trying to give you a visual of what we're solving for. So 1/125 to what power gets us 25? Okay, make them both powers of 5. So 5 to the negative 3x power equals 5 to the second power. Again, bases match. Exponents must match as well. So -3x is equal to 2. Divide by -3. And we get -2/3 as our answer. All right, next up, log base 1/16 of 1/64. So 1/16 to what power gets us 1/64? Okay, so let me just write that out. 1/16 to what power gets me 1/64. Okay, I can make them both powers of 4. They could also be powers of 2. I'm going to go with the 4. So 4 to the negative 2x power equals 4 to the negative third power. Okay, again, bases match, exponents match. So -2x is equal to -3. Divide out the -2. And we get 3/2. 3/2. Okay, next up here. 8 to what power gets me 2? I got to resolve that first before I can subtract away. Here, that log base 32 of 16. So I'm going to do this part first. 8 to what power gets me 2? Some of you might see right away, oh, it's a cube root, right? And if you see that, that's great. 1/3 really quickly. And if not, write it out. Make the bases the same. So 2 to the 3x power equals 2 to the first. 3x equals 1. Divide by 3. There's my confirmation. Okay, so here this simplifies to be just 1/3. Now over here, 32 to what power gets me 16. Okay, make them powers of 2. 2 to the 5x equals 2 to the 4th. So 5x equals 4. And this would clean up to be 4/5. Okay, so I've simplified each separate piece, but now I need to subtract, and I need a common denominator to do that. Here I have a 3, here I have a 5, so my common denominator must be 15. So here I'm going to multiply by 5/5 times 1/3, and here I'm going to multiply by 3/3 times 4/5. So 5/15 minus 12/15 is going to get me -7/15. Final answer. All right, next up, same deal. So here, log base 36 of 6. So again, maybe you see that a little bit faster, that the square root of 36 gets you to 6. So I'll do this one faster, right? That's just going to be 1/2. Over here, I have 16 raised to the power of log base 16 of 1/4. Okay, so remember that when the base of the logarithm here matches the base right here, right? I see that the 16s are the same. It really unlocks itself to get me just right here, whatever is that number in the argument position, the 1/4. So here this simplifies, right? Those 16s match. I get just 1/4 over here. It's an inverse property. Okay, and then here I am subtracting them. So I need 1/2 minus 1/4. So common denominator, I need this to be a 4 on the bottom. I'll multiply by 2/2. So here I get 2/4 minus 1/4, which will land me at 1/4. All right, next up, can you solve an exponential equation for x? So staring at this one, the first thing that I notice is that my bases can be powers of the same thing. I can make them both powers of 2. So 1/32 is 2 to the -5th. 64 is 2 to the 6th power. So I'm going to go ahead and rewrite that. 2 to the -5th power times 5 minus x, that's already there. Here 2 to the 6th power times 2x minus 7, that's already there. So again, once I get my bases to match, their exponents match too. So I'm going to distribute and get -25 plus 5x equals 12x minus 42. Okay, get the x's together. I'll subtract 5x from both sides, and then I'll add the 42. All right, so over here I'm going to get 17 equals 7x. Okay, divide each side by 7. Right, it's already reduced, so we'd say 17/7. Okay, you want to write that as 2 3/7. I will take that 2. If you want to give it to me as a decimal, 4 spots is good. So 2.4286 would be your decimal approximation to the nearest 10,000, 4 decimal spots. All right, next one. Can you rewrite the function in this format? So y equals a, that's our starting value, times 1 plus or minus the growth or decay rate as a decimal raised to t. T is years, usually years, right? The time that has passed. Okay, then can you state the growth or decay rate as a percent? Here decimals nearest 100, so 2 spots. Okay, so first thing to unpack here is that what I have here as my my base, my multiplier, 1.37, it's raised to the t over 4 power. That's like saying 1/4 of t. Let me rewrite it like that. Okay, so I'm looking at it as 1/4 times t. So then I'm going to crunch this portion of it, but still keep it to the t power. So here I'm going to type that into my calculator. What is 1.37 raised to the 1/4 power? It's like saying, what is the quartic root, the fourth root of 1.37? So here I'm just going to record that to 4 spots because I like my percents to 2 spots. So I'm going to record this as 1.0819 to the t power. So remember that what is right here is the 1 plus or minus r. Okay, so if I want to figure out if this is growth or decay, I see that it's more than 1, so it must be growth. This must be 1 plus r, right? So if I just take away the 1, I can see that my r, my rate, is about 0.0819 as a decimal, and then as a percentage, we'd say that that is about 8.19%. Okay, so if I write it in the structure, there's 2 ways we would take it. You could write that as y equals a times 1 plus 0.0819 to the t power, okay, or a times 1.0819 to the t power. Really take it both ways. Both are fine. So again, it's more than 1, so we know that that is growth, right? It's growing in value. And then here's my rate to the nearest hundredth, like that. So 8.19%. All right, next we are doing condensing and expanding of logarithmic expressions. Okay, so condense, that means that ultimately I want to take these separate terms and pack them into one. So the first thing that I see to do is to move the 4 back into the exponent position. Same with the 1/3. So I have log base 9 of x to the 4th power minus log base 9 of x plus log base 9 of x to the 1/3 power. Okay, then I want to fuse these first 2 terms into one. They're joined by subtraction, so I can make it log base 9 and make the argument position a quotient, a fraction, where I'm looking at x to the 4th divided by x to the 1st. So I have log base 9 x to the 4th over x to the 1st. So here I know that if I subtract the small from the large, that gives me x to the 3rd on top over 1, just x to the 3rd. So right now I have log base 9 of x to the 3rd power, and I still have plus log base 9 of x to the 1/3 power. All right, so if I want to fuse these 2 terms into one log, I can look at their 2 arguments and I can multiply them. I can make it a product. So now I have log base 9 x to the 3rd power times x to the 1/3 power. Okay, so here when I see that I have both bases here x, I need to add their powers, add their exponents. So I need to add 3 to 1/3, get a common denominator. So here I'll multiply by 3 over 3. So 9/3 plus 1/3 would be 10/3. So I'm going to end up with log base 9 of x to the 10/3 power. Just rewrite it over here. All right, final answer. Next, I'm going to expand. So I'm starting with this singular log, and I want to rewrite it like we saw over here. So first thing to do is to see that we have a quotient, right? I see that big fraction bar. So I'm going to separate these terms, and I'm going to write them as log base 3 y to the third power minus log base 3 81x. Okay, next thing that I see to do is pull the 3, the exponent of 3, back out in front. And I can also see that the 81x that's in the argument position here is a product, right? 81 times x. So I can take this log base 3 of 81x and write it as two separate logs that are being added. So let me write that out. 3 times log base 3 of y. Okay, minus, again, that's a product. So I'd say log base 3 of 81 plus log base 3 of x. But what I have to remember is that this right here is a package. So when I write it out in this next step, I have to make sure it stays as a package with parentheses. I can also see one more thing that I can resolve right here. I know that 3 to the 4th power gets me 81. So I can swap that out with just a 4. So I could write my answer just like this. I could say 3 times log base 3 of y minus parentheses 4 plus log base 3 of x. I would take that. That is fine. But you could also distribute out that negative 1 like that and write it as 3 times log base 3 of y minus 4 minus log base 3 of x. Okay, both of those would be correct. We'll take it either way. All right, let's look at the back. Okay, here we're given a series of equations, so exponential or logarithmic. We want to solve for x, simplify fractions, decimals 4 spots, so nearest 10,000, check for any extraneous solutions. Okay, we'll talk about that once it presents itself. All right, first up. So here I see that x is in the exponent position, e is the base. So I want to get this part of it right here all by itself. So I'm going to clear the fraction, multiply each side by 3. So e to the x minus 2 power equals 24. All right, I'm kind of stuck. So now I switch formats. I rewrite it as a log. So log base e of 24 equals x minus 2. Now log base e, we really just write that as ln. So natural log ln 24 equals x minus 2. Okay, and then the last thing that I'll need to do is add the 2 to the other side. Okay, and that can go straight in my calculator. So here I can say ln, natural log of 24. Okay, and then I'm going to add 2. Okay, and then I'm going to take it to the nearest 10,000. So I'm looking at what's in that 5th position right there. It's a 5, right? So that's going to pull the 0 to a 1. So I'll say, okay, that is about 5.1781. Okay, usually I put x right there too. All right, x is about 5.1781. Okay, next one, b. Here I see 6 times the natural log of x equals 18. So my first instinct is to divide that 6 away. Get the natural log of x by itself. But now I'm stuck. I can't type that into my calculator. So now I switch formats and I say, okay, my base here is e. E to the 3rd power equals x. Take it to the calculator. So here I hit second ln, e to the 3rd power. Here we go. So 20.0855. Okay, but maybe you saw this one a little differently. Let me show you an alternate pathway. Okay, maybe you thought, oh, I should first move the 6 into the exponent position. No problem. Then you would have natural log ln x to the 6th power equals 18. Okay, so now here, if I switch formats, I'd say e to the 18th power, okay, equals x to the 6th. Okay, and I'm trying to solve for x. So if I wanted to unlock here that x to the 6th power, I could raise each side to the reciprocal of 6, which is 1/6. And I'd get that x is equal to e to the 3rd power. Same thing that I have over here, just a different way of getting there. Okay, next one in C. Here I have 2 logs on the same side. And I know that even if I write it as 4 plus x, that's really x plus 4. So here, if these are being added, I can fuse them into one log by multiplying their arguments. So I really have log base 3 of x plus 6 times x plus 4 equals 1. Okay, so now I FOIL this out. First outer, inner last. Log base 3, x squared. 4x plus 6x is 10x plus 24. All in parentheses because it's still in the argument position, equal to 1. So now I have a log on one side equal to 1. The only thing I can do now is switch to exponential form. So 3 to the 1st power equals x squared plus 10x plus 24. Okay, I know that this is 3, so I'll subtract the 3 so that I can try to factor it. Okay, so 0 equals x squared plus 10x plus 21. So multiplies to 21, adds to 10. Got to be x plus 7 and x plus 3. So my two solutions would be -7 or -3. But let's double check. Let's say that I tried the -7 right here. That would give me a -1 in this argument position. So think about that. 3 to any power you can think of. Could that produce a negative in this position? Even if 3 was raised to something like -20,000, okay, that would give me a really, really small number, but it would still be more than 0, right? It wouldn't be something negative. So this one is extraneous. It is out. I'm making sure that whatever I get for x, when I plug it back into the argument position, it gives me something positive. And that -3 works in both of those positions. So x can only be -3. All right, next row here. Okay, here I have 5 to the -2x power minus 2 equals 17. So I want to get this part of it all by itself. So I'll add the 2 over. 5 to the -2x power equals 19. Now I'm stuck. 19 is not a power of 5. So now if I switch it to log form, I can say log base 5 of 19 equals -2x. And here I can use change of base. So log, it's now going to be a base 10. Log 19 over log 5. Right? They're both base 10, so my calculator can handle it. So always log of the argument over log of that base. Here, we're changing it to base 10 equals -2x. And I can type that into the calculator. So I can say log 19 divided by log 5. There we go. Gives me that decimal approximation. I usually record it to 4 decimal spots. It's nice and precise in my calculator. And then I just have to divide by 2. So divide by 2, right? Previous answer divided by 2. and here I'll take it to 4 spots. So x is about, let's see here. Oh, I needed to divide by -2. So this should be still a negative, right? Because that should be -2. So negative 0.9147. Yep. Final answer. Okay. Next up here, I see a log, 2 logs on the left and a log on the right. So first thing to do is fuse these 2 terms into one term. They're joined by subtraction. So I'm going to make their arguments into a quotient, into a fraction. So log x plus 4 over 2, right? The base is 10 when we don't write it, equals log 5x plus 1, right? That is all in the argument position. So now, since I have a log on each side of my equation, that means that their arguments would have to be the same as well. So my equation becomes x plus 4 over 2 equals 5x plus 1. Right? I'm solving for x, so I'd probably just clear my fraction. Right? This is like it's over 1. So multiply each side by 2. So x plus 4 equals 2 has to multiply over that 5x plus 1. So 10x plus 2. Okay. Combine your like terms. So take away x and then take away 2. So 2 equals 9x. Divide by 9. And we get that x is 2 over 9. All right, last problem here. I see log base x of 64 equals -3/2. Okay, switch to exponential form. X to the -3/2 power equals 64. Okay, I want to solve for x. So to get x to the first power, I can raise each side to the reciprocal. So I'm raising it to the -2/3 power instead. So x will equal the cube root of 64 raised to the -2nd power. So I know that that means I'm saying 4 to the -2nd power, which gives me just 1 over 16 as my solution. All right, last few are just word problems. Let me slide up to here. Okay, tried to pick some common ones that we've seen in this unit. So here, your parents need this much money. They need $42,000 in 10 years to help pay for college tuition for your brother. They can invest in an account with an interest rate of 4.75% that compounds continuously. That tells me we're using the PERT formula. We're going to see that E show up because it's continuous. How much should your parents invest today to have this amount in 10 years? So we know that the final amount that we want is $42,000. What we don't know is the principal amount that we need to invest times E raised to the rate 0.0475 T 10 years power, just like that. So we're trying to solve for the P. So here, if I multiply right here, E, right there, to the 0.0475 times 10 power, right? I'm going to record that to 4 spots just to keep it precise. That would be 1.608. But again, here I have it nice and precise in my calc. I see that really ultimately I just have to divide that away to find my principal. All right, so good steps showing my work. Now I take the 42,000 and divide that previous answer, so I'm not rounding till the very end of the problem, and here we go. So the initial investment would have to be $26,119.17. Okay, bacteria. Okay, so initial population of bacteria in a lab test is 500. So that's our starting value, our initial value. It grows at a rate of 80% every 15 minutes. Okay, so we have to keep that in mind. Every 15 minutes, it's growing at this rate of 80%, and we want to find the population at the end of 3 hours, and we're going to round to the nearest whole number. So what we have to remember is in 1 hour, so in 1 hour, there are 4 15-minute intervals, right, in 1 hour. So if I want after 3 hours, there's got to be 12 of them. So 12 15-minute intervals in 3 hours. Okay, so when I build it, I know that my final amount of bacteria, right, that's what I'm solving for, is going to be 500. That's my starting value, times 1 plus my growth rate, right? It was 80%, so 0.8 as a decimal, right? And it's going to have that growth 12 times in that span of 3 hours, because it happens every 15 minutes. And 15 minutes, that interval passes 12 times in 3 hours. Okay, I could just type in 1.8 right there as well. And then when I crunch it, so 500 times 1.8 to the 12th power, okay, is going to get me about 578,415.6907. But nearest whole number means I'm looking at what's in the 10th position right here, and that's going to pull this 5 to a 6. So 578,416 bacteria after that span of time. Okay, lastly, okay, here you have $5,000 to put in a savings account, earns 3.02% interest, compounded monthly, right? 12 months in 1 year. How long will it take for your investment to double, round to the nearest hundredth? Okay, 2 spots. So if my 5,000 doubles, it's going to be 10,000 at the end of this span of time. The initial amount was 5,000. This is compound interest. So 1 plus my rate of 0.0302 divided by 12, because it's compounding 12 times in the duration of a year, raised to the 12 times t power, right? So 12 times a year for how many years? Okay, now when I type this in, I got to keep parentheses around that fraction just to preserve the order of operations. So I know that here I'm going to first just divide out that 5,000. Okay, which makes sense. Here's 2 because my investment's supposed to double. And now I'm going to go ahead and just crunch 1 plus 0.0302. Don't need to close parentheses yet. Divided by 12. And yeah, we'll stop there because it still is raised to the 12t power. So here I would just record my steps, 1.0025. Again, I have it nice and precise in my calculator. And that's to the 12t power. All right, so now to solve it, I need to change it to log form. So I'd have log of what I just solved for. 1.0025 is my base of 2 equals 12t. Okay, here I would use change of base. So log 2 over log 1.0025 equals 12t. Okay, so whatever I get, I really just have to divide by 12. So I'm going to say here log 2 divided by log previous answer. Again, I like things precise. Okay, and once I get that, I'm going to record it, but I'm really dividing that by 12 to get to my final answer. So let me just record those steps so we have them. So we had the 275.7691 equals 12t, and then I divided that by 12, and then I'm taking it to the nearest hundredth, so 22.98 years. Right, that's what it looked like in the calculator. I'm just taking it to 2 spots. Okay, last question. So a fossil was found on an archaeological dig, contains 71% of its original carbon-14. We're given the function that models it, and we want to estimate the age. Hundredth is 2 decimal spots. Okay, so if we have currently 71% of the original amount, we would write that here for this part right there. We'd say 0.71 times n naught. That's just 71% of the original amount. Okay, rewrite this right-hand side of the equation. So n naught, whatever the initial amount is, times e to the negative 0.00012 t power. Now, if I divide that n naught from one side, it divides from the other side too. So I really just have 0.71 equals e to the negative 0.00012 t power. But now I'm stuck until I switch it to a log. So log base e of 0.71 equals negative 0.00012 t. But remember, log base e is really ln. So I'm just going to swap that out. And then I can plug that into my calculator and just divide out that negative 0.00012 from each side. Don't lose a 0. Okay. So now if I type that in, I have ln 0.71, okay, divided by negative 0.00012, okay, and we get a fossil that is about 2,854.09 years. All right, have a good day.